I'm going to get you to do is whatever color you chose for your coordinates, we are going to break up the unit circle into different families and figure them all out separately. So the first family is the axes family. Those are all the coordinates where the axes intersect the unit circle. And since it's a unit circle and the radius is 1, this is really easy to label the coordinates. My x coordinate would be 1, y would be 0. If I went up 1, 0, 1. If I went 1 to the left, it would be at -1, 0, and 1 down would be at 0, -1. We're going to put the degrees on here, and what we're going to do is we're going to choose a specific place to put degrees, a specific place to put radians. So I'm going to put my degrees on the line, so this would be 0 degrees. It's also 360 degrees, sort of close to the origin. So if in standard position I went to the positive y-axis, would you agree that that would be 90 degrees? Halfway around would be 180 degrees, and down here would be 270 degrees. I'm going to put radians in this section. So 0 is obviously still 0, but 360 degrees is 2 pi radians. Halfway around the circle, 180 degrees, we know that that's pi radians. 90 degrees is half of 180, so 90 degrees is pi divided by 2. And 270 degrees, right, if this is a half and this is 1, this would be like 1.5. We're going to write 1.5 as 3 over 2, because 3 over 2 is 1.5. That's really 390 degrees. I hope you can see 3 times pi over 2. That's the measure of that in radians. And we're now able to do some mental math using the big idea, and this unit circle and the family of angles is really going to do 2 of our big ideas. Big idea 1, any coordinates on the unit circle are cos theta, sine theta. So we're going to find out what that really means. And tangent is sine theta over cos theta. So we're going to use that idea to do some mental math. I need someone to volunteer to pick the first volunteer. So someone who doesn't want to answer the first question. All right, that was good. So my first question is this. What is sine of 90 degrees? And Jonathan's going to pick who's the volunteer to answer this. Patrick. Sine of 90 degrees. And the answers are on here. So we don't need a calculator. We're going to use the big idea. Sine of 90 degrees is 1. So the big idea says, if you know the angle, you can look at the coordinate, and the y-coordinate is sine. So sine of 90 degrees will be 1. What about cos of 180 degrees? Now, Betcha, you get to pick the next volunteer. Colin, cos of 180 degrees.
Would that be -1?
Be -1. So here we go to 180 degrees. We look at the coordinate. The x-coordinate is cos. You can try this on your calculator and find out. You now can do a bunch of easy mental math with 90, 180. Like I could say, let's do one more. Let's do sine of 270 degrees. Who are you going to pick? The hesitation is good. Teddy's got it.
Sine of 180, you said?
270.
270. -1?
-1. So we go to 270. We look at the coordinate. The y-coordinate is sine. So sine of 270 degrees is -1. We can also now do tangent. So I'm going to do tangent for each of these. I'm going to write it. I'm going to write the angle in radians. So tan of 0 is going to be sine over cos, 0 over 1, that's 0. Tan of pi over here. Sine over cos would be 0 over -1, which is 0. But what happens when I get to pi over 2? I mean, technically, if I write sine over cos, I get 1 over 0, which is
Not possible.
not possible. So we'll say not possible or undefined, any one of those things is good. And the same thing happens down here with tan of 3 pi over 2. It is also undefined or not possible. Still good.
Yeah, absolutely good.
You're good today, though.
Yeah.
Good. Okay. That is family number 1. Is everybody ready for family number 2?
No.
Almost?
No. I have a question.
Mm-hmm.
I still don't get this, how the sin and tan really works and combined with this. When you have normal sin of, let's say, 90 degrees, how is it just gonna be sin and then it's gonna be in the calculator? Is it good?
So if I go to my calculator, if I was in degrees, I'll make sure my calculator's in degrees, and I go sine of 90 degrees, I push enter, I get 1.
What about 270?
Sine of 270, I get -1. So what we're doing right now is we're extending the sine and cosine a little bit beyond what you originally learned. Originally, you learned right angle triangles, and sine was opposite over hypotenuse. What's the problem with 270 degrees? Draw me a triangle that has 270 degrees as one of its angles. Doesn't really work. So then we had reference angles. But even 90 is really problematic. Because, I mean, one of the angles in a right angle triangle is 90 degrees. And now you need the other angle to be 90 degrees. Okay? What is the other angle going to be if one's 90 and one's 90? The other one's 0. This doesn't really draw a triangle, so we have problems. But we can still do, and we still need to do math with angles like this as well. So then we define it by its circle. The x-coordinate is always cos, the y-coordinate is sine. Okay, family number 2. And our red dots are here, 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 and here. And this is the 30-degree family, 45-degree family. So the 45-degree family will be all of the angles where 45 degrees is the reference angle. So in quadrant 2, can you see if this was a 45-degree reference angle? You would go 180 minus 45, and this angle in quadrant 2 would be 135 degrees. In quadrant 3, I would go 180 plus a reference angle of 45, 180 plus 45 is 225 degrees. And in quadrant 4, I would go all the way around 360 minus my reference angle of 45 and get 315 degrees. In radians, 45 degrees is pi over 4. Do you remember the shortcut? Pi radians is 180 degrees. If you took 180 and divided it by 4, you'd get 45. So in radians, we would have pi over 4 radians. Now in quadrant 2, if you figured this out in degrees by going 180 minus 45, we now have to think the same way in radians. This second angle, does it make sense that if I went halfway around, that would be pi? And then I need to subtract my reference angle of pi over 4. How do we subtract fractions? We need a common denominator. So I'm going to change my pi to be 4 pi over 4 minus 1 pi over 4, and this angle is 3 pi over 4. Okay? How would you do the next one? You would have done in degrees 180 plus 45. Now in radians we'll go pi plus pi over 4. That would just change this to a plus sign, wouldn't it? And we would get 4 pi over 4 plus 1 pi over 4. 5 pi over 4. In quadrant 4, in degrees we went 360 degrees and then we subtracted 45. So in radians we're going to have to go all the way around, which is 2 pi, and we're going to have to subtract pi over 4. Again, we're going to need a common denominator. If I have this over 4, what would be on the top? An 8 pi. 8 pi minus 1 pi? 7 pi over 4. Unfortunately, the coordinates aren't obvious like the axes family. In the axes family, you just went over one, so it's easy to label. We have to somehow, though, get the coordinates without a calculator, because all of these values are values that you need to have memorized, and if you have to have them memorized, or they need to be able to be figured out without a calculator. So to do this, I'm going to introduce a special triangle for 45 degrees. Because to label the coordinates, I need sine of 45 degrees and cos of 45 degrees. So I go back to my grade 10 math and I say, well, I can get sine and cos if I have a right-angled triangle. And if I make one of these angles 45 degrees, what's the other angle in this triangle? Also 45, which makes this triangle special. It has a special name. What do we call this triangle? It's a right triangle, obviously, it's special for that. But if two of the angles are the same, we have a special name for that too. It's an isosceles triangle. And if the two angles are the same, the two sides are the same as well. Which means if I know one of the sides, I know the other one because it's the same. The math will work with whatever number you pick to go there. I'm going to choose a number that makes our mental math fairly easy, but you're not restricted to that. If you want to make your life miserable, put 3,852 as one side, and then the other side would be 3,852, and then you're going to have to do a squared plus b squared equals. Yeah.
Corey, I'm just dying over here.
Yeah, you're thinking of the mental math. I understand that. That would cause. So I'm just going to use 1. If that side's 1, this side's 1. Look, your coughing went away. Right? The mental math. Oh shoot. The mental math is better. 1 squared plus 1 squared is 2. This side will be the square root of 2. And from this, I can write that sine of 45 degrees has to be opposite over hypotenuse, 1 over root 2. And if I wanted to rationalize, I could. I could either write it as 1 over root 2 or root 2 over 2. Cos of 45, exactly the same. It'll be root 2 over 2 or 1 over root 2. Because cos is adjacent over hypotenuse. So if I take the 45 degrees, use the adjacent side and the hypotenuse, I'd get 1 over root 2. And tan of 45 is opposite over adjacent, 1 over 1. That will just be 1. I like using the tan over 45 to show you that it didn't matter what numbers you picked. For example, if you chose 5, the other side would be 5. What would tan be? 5 over 5, which is 1. What happens if we did the 3,182? The other side would be 3,182, and tan would be 3,182 divided by 3,182, which would be 1. The same thing would simplify with whatever hypotenuse you would have, but it would take you more work to simplify. Like if you used 5 and 5, the hypotenuse would be the square root of 50, which happens to be 5 root 2 when you simplify. And then if you would do 5 over 5 root 2, the 5s would cancel out and you would get 1 over root 2. And it works out no matter what. So I arbitrarily chose 1. It will work with whatever number you choose for the side. And now that we have these values, since the big idea says my x-coordinate is cos, my y-coordinate is sine, I now know that this coordinate is root 2 over 2, root 2 over 2. Then when I move to quadrant 2, my x-coordinate becomes negative. The numbers stay the same, but the signs change. In quadrant 3, can you see your x-coordinate's negative, your y-coordinate's negative? Both of these. Same numbers, but now they're both negative. And finally, in quadrant 1, your x-coordinate would be positive, but your y-coordinate would be negative. And from our special triangle, we know that tan of pi over 4, 45 degrees, is 1. In quadrant 2, that means that tan of 3 pi over 4, tan is negative in quadrant 2, is going to be negative 1. Can you still see that you could use the big idea? Sine of theta divided by cos of theta, you'd have root 2 over 2 divided by root 2 over 2, you'd still get 1. In quadrant 3, your cast rule says tan is positive. If you did sine divided by cos, a negative number divided by a negative number, you would get positive. And finally, tan of 7 pi over 4 is equal to negative. So it looks like there's a lot of things to remember, and there is, but there are patterns to help you memorize it. Like once you know quadrant 1 for the 45-degree family, you basically know everything else, just a couple of sign changes. Okay, who are we on for mental math? Who's the last person to answer? Teddy. So Teddy, you're going to pick a volunteer for, let's go, sine of 7 pi over 4.
Mateo.
Mateo.
Minus radical.
We can say radical or we can say root.
Root
2
2
over.
over 2.
Yeah. Perfect. So we got this one right here. What? Oh, should we up the level of difficulty of my questions just a little bit? Are you ready? A little bit more difficult? What if I ask you to do cos of negative 5 pi over 4? Cos of negative 5 pi over 4. Okay, you gotta pick a volunteer.
I need to pick again.
No, Mateo's turn.
Willie.
Willie. Cos of negative 5 pi over 4.
Can you say that again?
Mm-hmm. So we want to find cos.
Yeah.
And negative 5 pi over 4. Now, negative 5 pi over 4 is not listed. Negative angles still start here but go this way.
Yeah, I know.
So we have to figure out where is it going to end? What is it going to be coterminal with?
No, you have to say the minus the thing again.
Yeah. So we're going to find what is cosine, cos of negative 5 pi over 4.
Negative 5.
So basically this is 5 pi over 4 but with a negative.
Yeah, we need minus.
We say minus root. So we say for this we say root.
minus root of 2.
Mm-hmm.
Some fraction of 2.
It's good, eh? Yes, divided by 2.
Divided, okay.
Or divided by 2 or over 2.
Yeah, man, sorry.
Yeah, it's not English, right? But yes, now, so I want you to, when thinking of negative angles, do you see how 5 pi over 4 goes 3 quadrants in the positive direction? So when I say negative 5 pi over 4, you're going 3 quadrants in the negative direction. It is coterminal with 3 pi over 4. So then you're looking at your x coordinate there, you get the negative from that, and you get negative root 2 over 2. Of course, I could up it more. I could do different coterminal angles. I could say, what is sine of 101 pi over 4? Okay, all the way around once is 8. Twice would be 16. 3 times, 24, 32, 40, blah, 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 blah. Eventually you get here, 25. This would be 96. 100. Would 100 get us here? And then we'd have to go pi over 4 back. Wow. It's going to be in quadrant 3. 101 pi over 4 is coterminal with 5 pi over 4. And then you would be able to say that sine of 101 pi over 4 is y coordinate negative root 2 over 2. Ready for the next family?
No. Oh, yes.
The 30-degree family, draw your dots. For this one, I'm going to give you a 15-second head start to finish the degrees on your own.
Hey, where's, oh, that's good.
So can you label the other 3 degrees? Check how you did. Did you get 150 degrees, 210 degrees, and 330 degrees? All right, another head start for radians. If this is pi over 6, radians. Did you get 5 pi over 6, 7 pi over 6, and 11 pi over 6? And the special triangle for 30 degrees happens to also be the special triangle for 60 degrees. So in this space in between the two, we can write special triangle for 30 degrees and 60 degrees, because if I draw a right angle triangle and I make this angle 30 degrees, because it has to add up to 180, this will be 60 degrees. Question?
Why did it jump from 7 to 11?
Well, again, how would you figure out the 330 in degrees? You go all the way around 360 and minus 330 and minus 30. So we have to go in radians, all the way around in radians is 2 pi, minus my reference angle of pi over 6. Okay, and I have to get a common denominator,
Okay.
and I would get 11 pi over 6. Now, part of the reason it jumps is if this is 30 degrees, which is 1 pi over 6, would you agree this would be 2 pi over 6? Then 3, then 4, then 5, then 6, then 7. Then there'd be 8 here, 9, 10, 11 if they were all split up and you count it that way. So you can see why they're jumping more that way as well. Good question. Okay, so our special triangle for 30 degrees and 60 degrees, it's a right triangle, but we also have a name for a triangle if all the sides are different and all the angles are different. What is the name of that special triangle? Exactly, everybody forgets this one, because you're kind of like, it's not special, right? You remember it?
I do, I was just waiting for someone else to say it. Scaling.
It's a scalene. It even sounds kind of like scaly, I don't know, it sounds scalene. These are, it's like we give a special name for like, you're the triangle that's not special. Isosceles are feeling good. We got two angles and two sides the same. And then there's like, ooh, equilateral. We're all the same. We're super special. And then there's the scalene, which is kind of not special.
Which is the majority of circles
Yeah.
ever. I mean, not circles, triangles ever.
So this poor scalene triangle is feeling kind of bad. I'm not special. It's walking down the street and it bumps into another scalene triangle, just like them. In fact, perfectly the same. Same angles, same everything. And then one is like, I'm not special, and like, I'm not special either. And they become friends. In fact, they're inseparable. So I'm going to draw the friend right beside it. Here's its friend, also 90, also 30 up here, also 60 together. And when they get together, something special happens. Do you see that when they're together? They make a bigger triangle, which happens to be
Equilateral.
the equilateral. Which means all the sides are the same and all the angles are the same. So I can pick any number for this side. This side would be the same, and the bottom would be the same. Again, for nice mental math numbers, I'm going to choose 2, because then this is 2, and this whole length is 2, and it nicely splits up to 1 and 1. And now I can do a squared plus b squared equals c squared, and get the height to be the square root of 3. Which allows me, without a calculator, to do sine, cos, and tan of 30 degrees. Sine of 30, opposite over hypotenuse, 1 over 2. Cos of 30, adjacent over hypotenuse, root 3 over 2. Tan of 30, opposite over adjacent, and if you rationalize the denominator, you get root 3 over 3. And since it's also the 60-degree one, we'll write out the 60-degree family quickly as well. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So if we can draw the special triangle, we can get all of the values. And if we can get the values without the use of our calculator, this is something that we could do without our calculator. Those poor mathematicians before calculators, they were just trying to figure out everything without their calculator.
Yeah, I'm kind of curious as to what the method for figuring out one of the non-super simple angles would be, although that would probably take a lot of time.
Right. So one of the benefits of not having a calculator is they had to really come up with complicated math to figure out answers to simple questions. Like, what's sine of 40 degrees? So there's a couple of ways you could go about this. One, you could be very precise in your measurements. You could measure out 40 degrees perfectly, draw a right triangle, measure the opposite side, measure the hypotenuse, and say, I'm pretty confident it's close to this. But the problem with measurements is you could have human error. So then, how do we develop the mathematics to figure out those things? And this is just the start. So we're starting off, what can we find? We can find 0, 90, 180, 270, axes family, no problem. We now have special triangles. We can go to this one. And we know that cos of 30 degrees was root 3 over 2, sine of 30 degrees was 1/2. And now we can do all of these other values. Now my x coordinate would be negative, my y coordinate is still positive. Both of them are negative. Same thing from my triangle, I can find out, well, I know that tan of 30 degrees was root 3 over 3. So now I can label all the tan ones. So what is sine of 150 degrees? Willie, you get to pick someone.
I get to pick somebody.
Mm-hmm. 1/2. Perfect. So we go to 150 degrees. Sine is the y coordinate. We get 1/2. What about cos of 390 degrees? Amber, you gotta pick. Alyssa, you got picked. So first of all, we gotta figure out where 390 degrees is. 390 degrees is not on there, but it's coterminal with something. Did I say sine or cos? Cos of 390 degrees. Yes. So here's our 390 degrees. Cos is our x coordinate, root 3 over 2. Okay, let's do, you guys, right? I do this to really get you thinking about the big idea. Because we can say it's a big idea, but until we start to use it, we don't really think about it. Question?
I would just like to add that for any angle, they are going to be coterminal with waiting for any like what's the word?
Okay, good one.
What I'm trying to say is you can use modulus to figure it out.
Right, so if you would want to, like, if we're thinking in mod 360, right? Modulus math is like, the most common modulus math that people learn about is binary, because it's used in computers, which is a modulus of 2. Now, one modulus, this is an interesting, sorry, you got me off topic, got me interested in something. Modulus of 10 works out really good for humans because we have 10 fingers, right? So when we get run out of fingers, we got to do something about that. So we add another place, a decimal, like tens. We have a 1 and a 0 for 10. We use 2 numbers for the number 10, right? Because we run out of fingers, right? That's base 10 math. Computers work on just using zeros and 1. It's base 2. So they actually run out of numbers when they get to 1. They're like, what's next? 10. 10 means 2. Well, it's not actually 2, but it's 1, 0 in binary is 2 in regular math.
why wouldn't 1 be 2?
1, 1 is 3. Okay? So the way that binary works is similar to the way that regular numbers work. So let's start with regular numbers. Okay? When you have 235, these are our 1s. These are our 10s. 10s, that's not an S. Those are our 10s, or our 10 to the 1s. And these, in a base 10, are 10 squareds, or 100s. Technically, your 1s are technically 10 to the 0s. When you do to any other base, this is your 2 to the 0s. This is your 2 to the 1s. So if I wrote this number, this is my 2 to the 0s. This is my 2 to the 1s. This is my 2 squareds. This is my 2 cubes. And this is my 2 to the 4s. 2 to the 4 is 16. I have one of those. 2 squared is 4. I have one of those. And 2 to the 0 is 1. I have one of those. 16 plus 4 plus 1, this number in binary means 21. So for computers, they would recognize this as 21. Why do computers use binary? Because it's like the idea of switches. You can turn a switch on or off.
Yeah, computer programmers used just a huge array of a bunch of switches that
So-
you could automatically switch, and so they just kept using that coding.
Now, what's interesting about modular mathematics is one of the mathematicians, I think it was Boolean algebra, okay, developed this in the 1600s. And in the 1600s, he did a whole bunch of math with zeros and ones, and everybody was like, "You're insane.
I'm saying this.
When is anybody ever going to use this?" Then he died, and no one used it. Right? And his kids grew up, and they died, which they're like, "Yeah, well, my dad did stuff, no one used it, whatever." And now, technically, we, on a daily basis, we're using it more than any other math. Indirectly, because we have phones, we have every kind of technology running all the time, using zeros and ones. We're using it more than any other kind of math. But at the first time a mathematician looked at that was like hundreds of years ago. Maybe I should do some useless math for the next 20 years, and maybe hundreds of years from now it might be used. Sorry, that was off topic. We are on our last family, the 60-degree family. Let's draw our dots. So I guess the idea he was saying is that in modulus mathematics, we could take a mod 360. So 390 mod 360 is actually 30. And being actually 30, it's coterminal with 30. Okay, I'm going to write 60 degrees, and I'm going to write 503, and I'm going to give you a 30-second head start to do them both. If you're done already. Perfect. You already needed to know this for calculus, right?
Yeah, in fact, I have.
You have it from calculus.
Yeah.
How did you do? And then from the special triangle, We now know cos of 60 degrees is 1/2 and sine of 60 degrees is √3/2. So we can now label all of our points. And we can also do tan from our special triangle. Which means we are ready for our first quiz in this chapter, even though we have our test. We'll have it after our test of the other chapters. This quiz is a little bit different than the other quizzes you've had so far. This is not a take-home quiz. You have to do this in class. But I give you the quiz ahead of time. This is what your quiz looks like exactly. What your quiz basically is all 4 of these families put onto one page. So the first thing I would suggest is that you color code the families. For example, your 45 I did in green with a highlighter. I made my 60 degrees in yellow and my 30-degree family in blue.
So we're not allowed to write anything on the...
Yes, this is for you to write on. In fact, on the front page of this, I want you to copy everything that we have from these 4 families onto here. And fill the chart out at the bottom. The back part is for you to have a practice session. Now, what makes this different than other quizzes, it's going to be in class, it's going to be identical to this. But you have to get it all right. If you get it all right, you get 10 out of 10. If you make one error, you get 0 out of 10. However, after writing it for the first time on Tuesday, if you do make an error, you can redo it as many times as possible in 1 week until you get 100% without missing a negative, without leaving something blank, without mixing things up.
In lunchtime.
You can come at lunchtime or if you have a break during the day, but you have to get 100% on this. 100 or 0, that's the plan. If you noticed how things were, one thing you might have noticed, if you get quadrant 1, the other quadrants are easy. That's why color coding it is nice. We are also going to take all of this information and also transfer it onto a paper circle, paper plate circle. So we're going to, and this is going to be a project that's going to be due, I'll give you 2 weekends. Like this weekend you're going to be studying for your test. The next weekend you can have to, so I'll give you time to work on it. But you're going to transfer all of, here's the answer to the test, there's the answers to the test. You're going to transfer all of that information onto here. And we're going to,
Is there a time limit on this test?
sometimes I've done a time limit, like, do you want to do 10 minutes? No.
I
No.
don't want to memorize it, I'll just calculate it.
Well, you want to have some of it memorized. We should, because we do want to have it done
Yes,
fairly quick.
Okay.
So I'm going to give you a circle. Everybody gets one circle. Then we're going to go through some of the instructions together. 1, 3 more. Everybody gets 1 plate for free. If you screw up on your plate, you can make a donation to me that I give to Pros versus Joes. Minimum donation of 25 cents, so, and you can have another one. But we are going to go through.
What is pros and Joes?
It's a school activity that's coming up. So take your plate. Don't do anything until I demonstrate first, because otherwise you're gonna be donating right away. Short one. You may have more than one, just as a possibility.
Alright, there we go. Very hard to tell about that, I didn't realize.
So first thing, we have to fold it in half. Folding in half, you have to be careful. You're gonna fold it and you're gonna line up the edges and hold that tight. Because if you think you have it folded in half and don't hold that tight and press down, it might shift. And now you have a fold in a bad spot. So fold it over, make sure the edge lines up perfectly, hold that tight, squish it down somehow on your table. You can fold it back and forth both ways, and you will have cut your pie plate in half. And they're a little bit kind of bendy at the beginning, that's all right. They flatten out after the year if you keep them stuck in your book all year. Now, the second fold in half is trickier than the first fold in half. You're gonna, so I folded it in half this way. Now I'm gonna fold it in half the other way. Not only does the edge have to match up perfectly, but the fold from the one half has to match up with the fold on the other side. So this fold line matches up with this fold line. Hold that tight and press it down again. And you will get the perfect center to your pie plate with 4 quadrants perfectly at 90 degrees. Next, the suggestion is you're going to choose colors for your family. I suggested black for the Axis family. You can do whatever you want. Here's an example that I was showing you before. They made their Axis family nice and dark in black. This person decided to use the inside circle for their unit circle. I've seen sometimes people use the outside for their unit circle. Using the inside lets you write things on the outside. What we're going to do is we're going to transfer all of the information from our families and from our quiz onto here. And we're going to do it neatly. So, step 1, with a protractor. Don't own one, they exist on the internet, and a print button makes them amazingly, right? Or you can borrow one from me. take a protractor and from your center, measure out 30 degrees, 45 degrees, and 60 degrees. Draw your lines all the way straight through to make your families, okay? Each family is going to have its own colors. So here we've got like a blue, a green, and a purple for the families. Then you're gonna put all the information on there. And the color thing that I have on the paper, I'm going to give you a little creative license, okay? So, for example, in this one, this person did all of their radians in dark purple, all of their degrees in magenta, maybe. Their coordinates are in green, and tangents in blue. Okay, we'll just say blue. Okay? But I have another one here. Here's a good example. This person who made this pie plate, they decided to make their Axis family blue and black. They made their pi over 3 family orange, and then when they wrote everything in orange. But they made sure tangent was always in the same spot, coordinates always in the same spot, because you want to be able to have this to quickly get information off of. So I like this one because it's really neat, and the color coding lets me find answers quickly. I like this one a little bit, but some of it's not quite as neat. Like they color coded all of their degrees in the middle. And then they have, I really like how they made these big things of the Axis family, because I can pick this one up and I already know I should hold it like this. Whereas sometimes, like this one, I pick up and I don't know which way I should turn it. So it takes me a little while to find answers. Okay? So you've got some choice in color coding. Here's one where they made a dartboard and then they just have the answers in different parts of the dartboard, which made it really quick and easy to find. Although this one lost some accuracy mark because they wanted to make their dartboard look more like a dartboard. Their measurements, like it's supposed to be 30 and then 45 and then 60. Those, if you look on the one that's measured correctly, they're not the same distance between them, right? So they lost like a half a mark for accuracy, but it was worth it to make it look how they wanted it to look, okay? You're gonna make a legend. So on, for example, on the back of this one, they show the color coding as a legend. They gave it a name. This one's called Pie Face. And then they painted a picture of a blueberry pie with a slice taken out. Can you see that? It actually looks pretty good. It makes me kind of want a piece of blueberry pie right now. Okay? Some of the other one, like this one that I showed you. Oh, can you guess the name? This is spider web. Oh. Right? And they actually have across the here, if I turn it upright, starting right here, they have 3.14, and if you go all the way around, there's about 200 to 300 digits of pi listed around the outside of this spider web. Guessing names. Oh, there's some good. Let's see if you can guess. Can you guess the name of this one?
Squid.
Squid is close, but it's not a squid.
Octopus.
Close.
Octopi.
Octopi. Oh, groaner. Oh, the one that I couldn't tell. It has a snake on it. Any guesses? Python.
So it's just all puns.
Well, it's all puns, but sometimes I keep name fails too. This one is a name fail in my opinion. It's got the sun, it's nice, we've got the different planets. This one is called Planets. A little bit of a name fail, don't you think? It's like tried too hard, didn't quite work. And you don't have to have a name that, this is called Gary the Snail. That's the name of this one. There's Gary, Gary's food plate, Gary the Snail. With, this is an example of what happens when you start an idea at home on your paper plate and it fails miserably. And so you decide to make your own thing out of what materials you have at home. So we have Gary the Snail. Sometimes, this is just, the name is just the circle of life, but this person decided to do the 4 seasons in the 4 corners. They painted a tree on there, and if you look closely, like the leaves in these 3 are all made out of cloth and sewn on with a sewing machine.
Oh, what? Rad.
And the snowflakes too, they have little parts that are sewn on with a sewing machine. So that's a little bit of crazy. And then we have some ones that are bigger, like Bob Ross one over there in the corner.
Oh, that's someone's that was someone's project.
That was someone's project. And if you look at Bob Ross, like from afar, it looks like they may have just printed that out from the internet. That is all hand painted.
That's great.
Wow.
It is, yeah, it is wow, because it's like you go up there and even up close. Like some of my paintings look really good if you look from about 200 to 300 yards away. Then they're not bad. You get closer, they start, that one you get up close and you're like, even, wow, it's, so you should take a look at that. And then we have, like there's a artwork one on the top there. There, Van Gogh in the sun was the pie circle before, but then they needed to use it, so they took that part off and left the rest. Over here, here are some other examples of things that didn't even use the pie plate. Here is a working Ferris wheel. And someone made a piñata once. It was actually filled with candy. Yeah, a piñata. Yeah, right. I like this one. The name of this one is Pi R squared, but this sucker is round. That's just kind of fun, isn't it? Okay, so right now you're like, what the heck? Why did they go crazy like this? Okay, so there's a competition, okay? And the competition is, like, even though the prize isn't that big, the competition, I don't know, it goes crazy. Okay, the prize is 1 bonus mark on this unit test. Not the one that we're writing, but when we do the test for the circles, you get 1 bonus point on the test. There is up to 3 winners, right? Because sometimes if there's only 1 winner, people are like, nah. But there's 3 winners per class. The way that it works is after they're done, I put them out. I get random teachers that are walking by. I say, pick your favorite 5. If you get a first place finish, it's worth 5 points. Second place, 4 points. After I've had like 6 or 7 different teachers come by, I add up the points, and the top 3 get the bonus mark for the next test. So, oh, can you guess the name?
Pumpkin pie.
Pumpkin pie. Here we go.
You keep some of them?
I keep some of them so that I can show you. There was one person who made a working clock one year. But just flowers into the pie. Yeah. Oh.
Imagine if you write on it with a pencil you can't really erase anymore, and then it's completely wrong.
Mm-hmm.
You get 0 points.
Right. Anybody know what kind of fish this is? It's a pike. Okay.
Has anyone made the pun as far as the eye can see?
No, there you go.
I'm gonna take
Is that also one?
This one here?
No, the right one.
This one, yes, yes.
How's it called?
Street Fighter.
Oh.
instead of Street Fighter. So sometimes, yeah, right, sometimes we can get creative with the name, sometimes the name can fail, but still have fun. You don't lose anything for having a terrible name, but it makes me smile either way.
I think mine is pretty good.
Yeah,
I won, I got
you did get one. What was the title of that?
Fire in the Sky. I did with the moon and it had all the stars around it. I don't know what I'm gonna do with it.
So this is due.
This will be due, I will give you, like this weekend you're studying for the test. It'll be due after the weekend after that. So you have 2 weekends if you like. To be creative. That's gonna be on Tuesday. You don't have to hand it in, but on Tuesday, you'll sit in class and have to do it from memory. We will talk, maybe we'll do it on Wednesday. Cause I wanna talk about some strategies beforehand that'll help you. And Monday we have our test, so we can't really talk about strategies while we do the test. So let's do, this isn't test, this is just a little easy quiz.
So what is your favorite one, out of all? Personal favorite.
My personal favorite for using is the blueberry pie that I showed you, because I like it whenever I'm working in class, I'll pull this one out, because it's really easy to show stuff, and it's really neat and clear. Oh,
Like, that's for like showing,
right?
like.
It's hard to say favorite all time, like,
The Bob
Ferris
Ross.
wheel's super cool,
Yeah,
how
that's
it like turns and everything.
The
Bob Ross is
Right, I was like, no.
Inspires me.
like blow your mind crazy.
It's like.
So that's definitely
Yes.
one of the best all time.
It doesn't hurt. Anyway, what was a good one? That
Yes,
just
it is.
like.